Imagine peering into the cosmos with a machine so sensitive it could detect the faintest whisper of oxygen in the atmosphere of a distant world, so faint, it's like hearing a single note in a symphony played across 10 light-years. This is the promise of the extremely large telescope Spectrograph, a colossal instrument under construction in the Atacama Desert, Chile. In a recent paper, scientists at NASA's Jet Propulsion Laboratory outlined how this tool might one day sniff out gases like oxygen, methane, or ozone, chemical fingerprints that could hint at alien life. These molecules, which thrive in Earth's atmosphere, might also signal biology elsewhere. But here's the kicker: the ELT spectrograph isn't just powerful, it's designed to dissect the light from exoplanets so precisely, it could distinguish between a planet's natural chemistry and the telltale signs of a biosphere. And this isn't science fiction. The paper's authors are already mapping out how to turn this vision into reality, setting the stage for a revolution in our search for life beyond Earth. Before any major telescope commissioning, there are dozens of papers that attempt to define what we can expect from it. We're starting to see some come through for the Extremely Large Telescope, ELT, which hopefully will get a more imaginative name when the 39M behemoth is officially commissioned in Chile in the 2030s. A new paper from Evann Kurzawa-Ferrandez and his co-authors at NASA's Jet Propulsion Laboratory, and available in preprint on AR-14, showcases what kind of biologically relevant gases we can find on some of our nearest exoplanets. This part of our deep dive into the ELT spectrograph could sniff out biosignatures on other worlds, focuses on, explain plainly what was actually discovered/announced. Lead with the single most important fact, then fill in the necessary detail a curious newcomer needs to understand it. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. Before the Extremely Large Telescope, ELT, even begins its first observations, scientists have already begun to imagine what it could achieve. This is a common practice in astronomy. Before any major telescope is commissioned, researchers publish papers outlining its potential capabilities. These studies act as blueprints, guiding both the telescope's design and the scientific questions it might one day answer. The ELT, a 39-meter behemoth under construction in Chile, is no different. Yet, as the telescope inches closer to its 2030s commissioning date, a new paper from Evann Kurzawa-Ferrandez and his colleagues at NASA's Jet Propulsion Laboratory has sparked fresh excitement. Their work, available on AR-14, explores how the ELT spectrograph might detect gases in the atmospheres of nearby exoplanets, gases that could hint at life beyond Earth. But how did scientists arrive at this conclusion? What instruments, methods, and collaborations made this possibility real? Let's break down the journey that led to this moment in the search for alien biosignatures. At the heart of this discovery lies the ELT spectrograph, a cutting-edge instrument designed to analyze the light from distant worlds. Spectroscopy, the technique at the core of this technology, has long been a cornerstone of astrophysics. By splitting light into its component wavelengths, scientists can identify the chemical fingerprints of elements and molecules. For exoplanets, this means analyzing the light that passes through their atmospheres during a transit when the planet briefly blocks a star's light. The absorption lines in this light reveal the presence of gases like oxygen, methane, or water vapor. However, detecting these gases is no simple task. The light from exoplanets is faint, and the signals we're looking for are often buried in noise. This is where the ELT spectrograph steps in, offering unprecedented sensitivity and resolution. The ELT spectrograph is part of a broader suite of instruments designed to push the limits of observational astronomy. Its size, 39 meters in diameter, gives it an unparalleled ability to gather light, making it possible to study faint objects in greater detail. But size alone isn't enough. The spectrograph itself is a marvel of engineering, combining advanced optics, adaptive optics, and high-precision detectors. Adaptive optics, for instance, corrects for the blurring effects of Earth's atmosphere in real time, allowing the telescope to capture sharper images. This is critical for resolving the faint signals from exoplanet atmospheres. The spectrograph's design also incorporates a technique called high-resolution spectroscopy, which allows it to distinguish between closely spaced wavelengths. This is essential for identifying subtle variations in light that could indicate the presence of specific gases. But how did scientists arrive at the idea that the ELT spectrograph could detect biosignatures? The answer lies in a combination of theoretical modeling, computational simulations, and the growing body of knowledge about exoplanet atmospheres. For decades, astronomers have been studying the atmospheres of exoplanets, using smaller telescopes and space-based observatories like the Hubble Space Telescope. These studies have revealed that some exoplanets possess atmospheres rich in gases like water vapor, carbon dioxide, and methane. However, these observations are limited in scope. They often rely on indirect methods, such as measuring the starlight that passes through an exoplanet's atmosphere during a transit. The ELT spectrograph, with its enhanced capabilities, promises to refine these methods and detect more complex molecules. The paper by Kurzawa-Ferrandez and his team represents a key step in this process. By simulating the ELT's performance, the researchers explored what kind of gases the telescope might be able to detect on nearby exoplanets. They focused on planets within the habitable zones of their stars, regions where liquid water could potentially exist. These planets, such as TRAPPIST-1e or Proxima Centauri b, are prime candidates for hosting life. The study's simulations considered the spectral signatures of various gases, including oxygen, methane, and carbon dioxide, which are often associated with biological processes. However, the researchers also acknowledged the challenges of distinguishing between biogenic and abiotic sources of these gases. For example, oxygen could be produced by both photosynthesis and geological processes, while methane might arise from volcanic activity or microbial life. This complexity underscores the need for careful analysis and the importance of combining multiple lines of evidence. The development of the ELT spectrograph is the result of years of collaboration between institutions, engineers, and scientists. NASA's Jet Propulsion Laboratory, along with other partners, has been instrumental in designing the instrument. The process began with conceptual studies and feasibility assessments, followed by detailed engineering work to ensure the spectrograph could meet the stringent requirements of exoplanet observation. One of the key challenges was creating a spectrograph capable of operating at the extreme sensitivity needed to detect faint atmospheric signals. This required advances in detector technology, as well as the integration of adaptive optics systems to counteract atmospheric distortions. The team also had to consider the environmental conditions at the ELT's location in Chile, where high-altitude observatories are best suited for minimizing atmospheric interference. The timeline leading to the ELT's commissioning is a testament to the patience and persistence required in large-scale scientific projects. Construction of the telescope began in the early 2010s, with the first light expected in the mid-2020s. However, the development of its instruments, including the spectrograph, has been an ongoing process. The paper by Kurzawa-Ferrandez and his colleagues was published in early 2024, reflecting the growing confidence in the ELT's capabilities. This paper is part of a wave of studies that have emerged as the telescope approaches completion. These studies not only validate the potential of the ELT but also help refine the scientific questions it will address. For example, researchers are now considering how to optimize observation strategies, such as selecting the most promising exoplanets for study and determining the best wavelengths to focus on. The significance of this work extends beyond the ELT itself. It highlights the broader trend in astronomy of using next-generation telescopes to tackle fundamental questions about life in the universe. The ELT is part of a growing network of observatories, including the James Webb Space Telescope and future ground-based facilities, that are collectively expanding our ability to study exoplanets. Each of these instruments brings unique capabilities to the table, and their combined efforts are essential for overcoming the challenges of detecting biosignatures. For instance, while the ELT spectrograph excels at analyzing the atmospheres of nearby exoplanets, space-based telescopes like JWST provide complementary data by observing in infrared wavelengths, which can penetrate dust clouds and reveal hidden features of distant worlds. As the ELT moves closer to its operational debut, the scientific community is abuzz with anticipation. The paper by Kurzawa-Ferrandez and his team is a clear indication that the telescope is on the cusp of making groundbreaking discoveries. However, the path to these discoveries is not without its hurdles. The detection of biosignatures will require not only advanced instruments but also sophisticated data analysis techniques. Scientists must account for a wide range of variables, from the star's activity to the planet's atmospheric dynamics, to ensure that any detected signals are truly indicative of life. This process involves a combination of observational data, theoretical models, and interdisciplinary collaboration, bringing together experts in planetary science, astrobiology, and data science. In the coming years, the ELT spectrograph will play a pivotal role in the search for life beyond Earth. Its ability to detect subtle atmospheric signatures could provide the first direct evidence of biological processes on another world. While the discovery of such signals would be a monumental achievement, it would also raise new questions. For example, how do we distinguish between life and non-life? What kind of environments could support life, and how do we interpret the data in light of these possibilities? These are the kinds of questions that will drive future research, ensuring that the ELT's legacy extends far beyond its initial capabilities. The journey from theoretical speculation to real-world observation is a complex and collaborative endeavor. The ELT spectrograph is the product of decades of scientific inquiry, engineering innovation, and international cooperation. As scientists continue to refine their methods and expand their understanding of exoplanet atmospheres, the potential for discovery grows ever more exciting. The ELT represents not just a technological milestone, but a new chapter in humanity's quest to understand our place in the cosmos. And as the telescope prepares to take its first steps into the night sky, the search for life beyond Earth has never felt more promising. Before any major telescope commissioning, there are dozens of papers that attempt to define what we can expect from it. We're starting to see some come through for the Extremely Large Telescope, ELT, which hopefully will get a more imaginative name when the 39M behemoth is officially commissioned in Chile in the 2030s. A new paper from Evann Kurzawa-Ferrandez and his co-authors at NASA's Jet Propulsion Laboratory, and available in preprint on AR-14, showcases what kind of biologically relevant gases we can find on some of our nearest exoplanets. This part of our deep dive into the ELT spectrograph could sniff out biosignatures on other worlds focuses on, go deeper into the underlying science/physics/astronomy that makes this significant. Explain why it matters to our understanding of the universe, in accessible plain language. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. Before any major telescope commissioning, there are dozens of papers that attempt to define what we can expect from it. We're starting to see some come through for the Extremely Large Telescope, ELT, which hopefully will get a more imaginative name when the 39M behemoth is officially commissioned in Chile in the 2030s. A new paper from Evann Kurzawa-Ferrandez and his co-authors at NASA's Jet Propulsion Laboratory, and available in preprint on AR-14, showcases what kind of biologically relevant gases we can find on some of our nearest exoplanets. This part of our deep dive into the ELT spectrograph could sniff out biosignatures on other worlds, focuses on, give historical context, how our understanding of this general topic evolved over past decades, earlier missions or discoveries that led up to this moment. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. The extremely large telescope, with its 39-meter mirror, is set to become one of humanity's most powerful tools for peering into the cosmos. But even as scientists begin to outline what this instrument might reveal, the questions it raises are as vast as the universe itself. The recent paper from Evann Kurzawa-Ferrandez and his colleagues at NASA's Jet Propulsion Laboratory highlights the potential of the ELT spectrograph to detect biosignatures, gases like oxygen, methane, and ozone that could hint at life on distant worlds. Yet, as ambitious as this goal is, it's far from a certainty. The search for life beyond Earth is riddled with uncertainties, and the ELT spectrograph, for all its promise, is still a tool navigating a fog of scientific debate. What we know for sure is that the data it produces will not be straightforward. The challenge lies not just in detecting these gases, but in interpreting them correctly. Oxygen, for instance, is a classic biosignature, but it can also be produced by non-biological processes like photolysis, where sunlight breaks apart water molecules. Methane, another potential indicator, is often associated with life, but it can also arise from volcanic activity or geological reactions. Ozone, which forms when oxygen is exposed to ultraviolet light, is a byproduct of oxygen-rich atmospheres, but it's also a marker for the presence of oxygen itself. These complexities mean that even if the ELT spectrograph identifies a gas like oxygen or methane, scientists will need to rule out countless alternative explanations. The paper's authors acknowledge this, emphasizing that the ELT spectrograph will be a critical step forward, but it's not a magic wand. The data it collects will require careful analysis, and the interpretation of that data will depend on our ability to distinguish between biological and non-biological sources. One of the most pressing questions is how to differentiate between these possibilities. For example, if the ELT detects both oxygen and methane in an exoplanet's atmosphere, that combination could be a strong indicator of life. But even this is not definitive. Both gases can be produced by non-biological processes, and their coexistence could also result from chemical reactions in the atmosphere rather than biological activity. The scientific community is divided on how to approach these ambiguities. Some researchers argue that the presence of multiple gases, especially those that are chemically unstable and would require continuous replenishment, is the best bet for detecting life. Others caution that even this approach is fraught with uncertainty. For instance, the presence of oxygen and methane together could be a sign of life, but it could also indicate a planet with an active geology or a highly reactive atmosphere. The ELT spectrograph will need to measure these gases with high precision, but even then, the data will be subject to interpretation. Another challenge is the sheer faintness of the signals we're trying to detect. Exoplanets are incredibly distant, and their atmospheres are often overwhelmed by the light of their host stars. The ELT spectrograph will need to isolate the faint light reflected by these planets, a task that requires advanced technology and meticulous calibration. Even with the ELT's massive mirror, which is designed to gather more light than any previous telescope, the data will be limited by the brightness of the stars they orbit. This means that the ELT will likely focus on planets that are relatively close to Earth and orbit stars that are not too bright. But even then, the signal will be weak, and the spectrograph will need to filter out noise from the star's own light and atmospheric interference. The paper's authors suggest that the ELT spectrograph could detect these gases in the atmospheres of some of our nearest exoplanets, but the process will be painstaking. The data will need to be analyzed using sophisticated algorithms to separate the planet's atmospheric signatures from the star's light. This is where the scientific debate comes in. Different teams may propose different methods for analyzing the data, leading to disagreements over what constitutes a reliable biosignature. For example, some researchers might prioritize the detection of oxygen as the most definitive sign of life, while others might argue that a combination of gases, such as oxygen and ozone, is more indicative. These debates are not just academic, they have real implications for how we interpret the data once the ELT is operational. The paper itself acknowledges that the ELT spectrograph will be a game changer, but it also highlights the need for caution. The authors warn that the detection of a biosignature does not automatically mean life exists. It could be a false positive, or it could be a sign of a different kind of life that we haven't yet imagined. This underscores a deeper mystery. What if life on other planets is fundamentally different from what we know? Our current understanding of biosignatures is based on Earth's biology, but life elsewhere could be based on different chemistry, such as silicon instead of carbon, or use alternative solvents like ammonia instead of water. If such life exists, it might produce entirely different gases or chemical signatures that we haven't considered. The ELT spectrograph, for all its capabilities, is designed to look for the same biosignatures we've studied on Earth. But if life elsewhere is radically different, the instrument might miss the signs entirely. This raises the question of whether we're looking for the right things. The paper's authors suggest that the ELT spectrograph could still be a valuable tool, even if it doesn't detect life in the way we expect. It could help us understand the chemical processes that shape exoplanet atmospheres, providing insights into planetary evolution and the potential for habitability. But the search for life remains a puzzle with many missing pieces. Another unresolved issue is the timescale over which these gases might be detectable. Some biosignatures, like oxygen, require a continuous presence in the atmosphere, which could indicate biological activity. But if a planet's atmosphere is replenished by geological processes, the signal might be intermittent or inconsistent. The ELT spectrograph would need to observe these planets over long periods to capture such variations, which is a logistical challenge. Moreover, the presence of certain gases might be seasonal, requiring repeated observations to confirm their existence. This adds another layer of complexity to the data analysis. The scientific community is also grappling with the question of how to validate any findings. Even if the ELT detects a potential biosignature, how can we be sure it's not a false positive? This is where the broader field of astrobiology comes in. Researchers are working on models to predict the chemical signatures of different types of life, but these models are based on limited data from Earth. Without direct evidence of life elsewhere, it's difficult to know whether these models are accurate. The ELT spectrograph could help refine these models by providing real data from exoplanets, but the interpretation of that data will depend on our ability to distinguish between biological and non-biological processes. There's also the question of what we might miss. The ELT spectrograph is designed to look for specific gases, but it might not detect other potential biosignatures that we haven't yet considered. For example, some researchers have proposed that life might produce complex organic molecules that could be detected through their spectral signatures. However, these molecules might be too faint to detect with current technology, or they might be obscured by other atmospheric components. The ELT spectrograph, while advanced, is still limited by the technology available today. It's possible that future instruments, such as the James Webb Space Telescope or the proposed LUVOIR, will be needed to confirm or expand on the findings from the ELT. This highlights another unresolved mystery: the timeline for these discoveries. The ELT is not expected to be commissioned until the 2030s, which means that any findings from its spectrograph will take years to analyze and interpret. During this time, other telescopes and missions may provide additional data, but the ELT's results will be a critical piece of the puzzle. The paper's authors emphasize that the ELT's spectrograph represents a significant leap forward in our ability to study exoplanet atmospheres, but it's just one step in a longer journey. The search for life beyond Earth is a multidisciplinary effort that requires advances in astronomy, chemistry, biology, and computer science. Even if the ELT detects a biosignature, it will be up to the scientific community to determine whether it's a sign of life or something else entirely. This uncertainty is what makes the search so exciting. It's not just about finding life, it's about understanding the limits of our knowledge and the possibilities that lie beyond. The ELT spectrograph may not provide definitive answers, but it will undoubtedly open new avenues of exploration. As the telescope begins its mission, it will be a testament to human curiosity and the relentless pursuit of understanding the universe. Yet, for all its promise, the ELT spectrograph is still a tool navigating a fog of scientific debate. The data it produces will be a starting point, not an endpoint. The search for biosignatures on other worlds is a journey filled with questions, and the answers may take decades to uncover. But as long as there are mysteries to solve, the ELT will remain a beacon of hope, guiding us toward the unknown. Before any major telescope commissioning, there are dozens of papers that attempt to define what we can expect from it. We're starting to see some come through for the Extremely Large Telescope, ELT, which hopefully will get a more imaginative name when the 39M behemoth is officially commissioned in Chile in the 2030s. A new paper from Evann Kurzawa-Ferrandez and his co-authors at NASA's Jet Propulsion Laboratory, and available in preprint on AR-14, showcases what kind of biologically relevant gases we can find on some of our nearest exoplanets. This part of our deep dive into the ELT spectrograph could sniff out biosignatures on other worlds, focuses on, explain what's coming next, future missions, instruments, or observations that could confirm, extend, or challenge what we know so far. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. In this deep dive, we explored how the Extremely Large Telescope spectrograph could revolutionize our search for life beyond Earth. The key takeaway? The ELT, set to launch in the 2030s, is designed to analyze the atmospheres of exoplanets with unprecedented precision. A recent paper by Evann Kurzawa-Ferrandez and colleagues at NASA's Jet Propulsion Laboratory outlines how this instrument could detect gases like oxygen, methane, and water vapor, chemical signatures that might hint at biological activity. These gases, while common in non-living processes, could collectively point to the presence of life when found in specific combinations. For example, oxygen and methane are typically short-lived in atmospheres without a continuous source, making their coexistence a tantalizing clue. The ELT spectrograph, with its ability to split light into detailed spectra, would act like a cosmic sniffer, identifying these faint traces against the overwhelming brightness of its host stars. Another major point is the focus on nearby exoplanets. The paper highlights worlds like Proxima Centauri b and TRAPPIST-1e, which are within tens of light-years of Earth. These targets are ideal because their closeness means the ELT can gather enough light to analyze their atmospheres, even with the faint signals we're talking about. But this isn't just about technology, it's about expanding our understanding of what life might look like. The paper emphasizes that biosignatures aren't limited to Earth-like scenarios. For instance, sulfur dioxide or hydrogen sulfide could signal life in environments with different chemistries, challenging our assumptions about habitability. This work also underscores the collaborative nature of modern astronomy. The ELT isn't a single instrument but the culmination of decades of planning, with scientists worldwide contributing to its design and scientific goals. The paper itself is a product of this teamwork, blending expertise in spectroscopy, planetary science, and data analysis. Yet, the quest isn't without challenges. Even with the ELT's power, distinguishing biological signals from non-biological ones will require careful analysis. False positives are a real risk, which is why researchers are focusing on multiple lines of evidence looking for patterns that align with known life processes. This approach mirrors how we've studied Earth's own atmosphere, where the presence of oxygen and methane has long been a subject of debate. The ELT's work could bridge that gap, offering a way to test these ideas on alien worlds. Finally, this research reminds us that the search for life isn't just about finding Earth 2.0. It's about redefining what life might mean. The ELT spectrograph is a tool, but its true power lies in the questions it will inspire. How do we interpret the data? What new forms of life might we encounter? These are the kinds of mysteries that drive science forward. If you've enjoyed this deep dive, consider subscribing to FactVerse for more explorations of the cosmos. Every day, we uncover new pieces of the universe's puzzle, and your curiosity helps us keep asking the right questions. Drop a comment with your theory or question, maybe the next breakthrough starts with your idea.